So today for our public talk, Rich Wolski is going to talk about Pubsub, publish subscribe model and its uses. And Rich is a computer science professor at the University of California, Santa Barbara, who's been working in SCiMMA for the last couple of years, helping us leverage the fruits of computer science research, particularly with respect to the cloud and also operating in a distributed software development environment. So if you want to take it away, Rich.
Yes, thank you. And thanks everybody for coming. Let's see if I can do the screen share thing here effectively. We'll take care of that. And we'll put it into presentation mode, which then requires a little bit more of this. Okay, thanks again for coming. Adam and Patrick and some of the other potentates for SCiMMA asked me to talk a little bit about Pubsub, in a more general context, and then try to relate it to MMA. I think giving a talk to an auspicious body such as this one about MMA when I don't know much or anything really about astronomy would be foolish. So there's going to be very little astronomy. No astronomers or astronomical concepts were harmed in the making of this talk. But I will try and provide what the problem set that I've seen over the last couple of years in working with my distinguished colleagues on SCiMMA looks like to a computer scientist who's spent a fair amount of time thinking about things like cloud computing. All right, so let's start with this notion of publish subscribe. This is a computer science perspective on what Pubsub architectures do. They are really attention focusers. And they're attention focusers when there's a data set, which is an abstract concept, and that data set is changing dynamically, so that one's attention needs to be focused temporally. It's an old idea in computer science. Computer science is not very old, so we think of things as being, that are 20 years old as being ancient. It's originally due, they think, to Berman and Joseph from SOSP 87. This is a big operating systems conference in computer science, but it really became something that people thought about in more than academic terms with Google and Netscape. RSS, which stands for Really Simple Syndication Protocol, is basically a protocol that obviated the incredibly taxing activity of having to type keywords into the Google box by typing them in for you periodically and sending you the results. And there needed to be a protocol to do that. There's been since then something called Adam, which is essentially a replacement improvement on RSS. But the big idea was that internet search, this is what got everybody excited. Internet search was creating this dynamically changing world, this dynamically changing data set. And rather than constantly searching it yourself, you would like to have something narrow the scope of that search, focus your attention on things that really matter. Okay, abstractly then, we can think about this. This is sort of how it looks to us as computer scientists, as really kind of three concepts. There are publishers. Usually they're distributed in this world, and they're collectively updating a shared corpus of data. Update can either be update, which is with replacement, or append only. We're adding to some large data, and it may be a combination of both. Data may append and then age, and then the subscribers, which are interested in a subset of the data. The data can be structured, in which case the subscriber wants a join in database terms from various objects. Or unstructured, in which case it's some form of key value, where there's a ragged collection of bits and then an identifier for it, and then we can do things, with selections from the identifier. So, and then importantly, the subscriber specifies some sort of quality of service constraint on the subscription. There are typically 4 that we think about, which not in any order of preference. At least once, which means if something gets published, it will be delivered to a subscriber at least once, but maybe more than once. At most once. This was the original RSS QoS specification, which is duplicates will be suppressed. You won't see the same thing twice, but you may miss things. Exactly once, which is what everybody really wants from a Pubsub system. It's essentially akin to ACID database semantics. It can be done. It actually is something that requires some work. You usually do at least once with data deduplication. That gets you exactly once semantics, but there's a latency penalty. And then best effort, which is kind of your internet search thing, where you go and you search the internet and you assume that there's a high quality search engine, which is prioritizing your attribute-based search, but things may be missed. And then this notion of a data set is abstract. It's not a database. It's not a single maybe amalgamated storage infrastructure. It can be decentralized, distributed, very, very distributed, in fact. But in some sense, the data is being contributed to this corpus. All right. There's really sort of three patterns in computer science, programming terms that Pubsub comes in. The original and the one that sort of made the most sense to at the beginning was multicast. Networking people for a while have been trying to build into the networking infrastructure the idea of selective broadcast. With the QoS, Pubsub becomes reliable synchronous multicast or reliable broadcast, i.e. you can tell when a broadcast has reached some set of consumers for the QoS purposes. And Ken Bierman's original paper was about group membership, which is a way to do synchronous reliable multicast. You build a lot of Pubsub systems. A lot of Pubsub systems are really just database systems where subscribers periodically subscribe to the data. Maybe they get a callback, maybe they don't. But the key thing that you have to add to the database is some notion of clock. You don't, especially if you're doing duplicate suppressing, once something has been added to your database, you only want to see it after it's been updated. So there's some notion of what you've seen and what you haven't seen. And then the third style, which is the hardest to scale, but the one that you sort of would like to have is one where you register some notion of interest, and then there's an alert. And that alert is sent to you. Hopefully it's sent only to you. So securing it can be a bit of a chore. But it's asynchronous in the sense that you get the alert maybe with some QoS on how soon after the data has been published, maybe not. And in programming terms, we call this a callback. And then there's kind of two ways to express interest. So these are three ways to get the data. There's kind of two ways to express interest. You can furnish the system with a description of what the data looks like that you are interested in, and it's an imperfect specification. Streaming databases is kind of the buzzword that people use for this today, which is where instead of querying a database that's been updated, you add a query, and as the data flows through the database, if it matches the query, you get an alert. That's really a Pubsub paradigm, but it's content-based. It's really based on attributes. And then the more popular one is topic-based, where we're going to categorize the data manually, or maybe with AI someday. But the data all falls under some, the data that you're interested in falls under some rubric that you can specify. And then there's questions about what if you want data from multiple topics and so on and so forth. There's a whole composition question that topic-based things bring up. But it's by far the more popular of the two, and usually the categorization is the main one. There's a couple of different ways that you build these systems. Broadly speaking, you can think of them as protocol-based, where either the network, IGMP or AMQP, are providing messaging protocols that you can use, and the key there is that the routing is usually decentralized. IPv6 has multicast built into it, but there are restrictions sometimes on these protocol-based things having to do with how many publishers there can be and various access control or lack thereof issues. The way that most people do this is through some sort of middleware, which is loosely termed, broker based. In the programming world, this Pubsub notion exists, and it's not distributed. It's not something that people put networks into. Java Enterprise Service Bus is probably the best example. It uses JMS, which is a messaging protocol, but it's this idea that you can build Java programs and then use the class signatures essentially to register things that you can produce, or to find things that you wish to consume as parameters, within the context of a single program or system. And there's something called Pi Message Bus, which I don't know much about. There are commercial products called, one that I've used before is called MuleSoft. And they usually have network extensions, but these extensions are usually proxy kinds of technologies. They don't work great in a network. Proxies are difficult. But it's the same idea. There are database approaches. Postgres and MySQL both support Pubsub paradigms, messaging paradigms, so that you can get triggers and so on and so forth when things are published and there are updates and so on and so forth. But a lot of the community, and this is where scientists typically start with a database and then build out the data acquisition and the data distribution pieces of it. That's fairly common. The cloud does this in a couple of different ways. The cool kids today get some sort of scalable database like DynamoDB, which is a NoSQL but very, very scalable database. And then they take a separate system, a functions as a service system, which is a triggered computation model that can communicate with DynamoDB, say in Amazon. You upload computations into the functions as a service, which do the filtering. But there are also queuing services. There's a legacy system that Amazon, for example, supports called SQS, and it's basically a Pubsub architecture, but it's within the cloud only. And then there are middleware services. Kafka, the one that SCiMMA has been focused on, is an example of such a service, but there are others. RabbitMQ, open source, currently curated by VMware. MQTT is an IoT protocol, but all its implementations are broker-based. It's really a middleware. That's kind of the same thing that Kafka wants to be for IoT, and there's something for low-power IoT called MQTSN. And then there are peer-to-peer systems, and this is a very computer sciencey thing, but we're starting to see it more and more. There are things like distributed hash tables, CRDTs, conflict-free replication. Replicated data types. CRDTs is how you do collaborative editing, which we do a lot of on the SCiMMA project. That's actually the data structure, distributed data structure that Google uses behind the scene. And it does a Pubsub protocol. So there's lots of ways to skin this cat, from a messaging pattern perspective, from an architectural perspective, abstractly. This is from Andy Howell. Thank you, Andy, if you're on at LCOGT. This is kind of what MMA looks like for transient follow-ups. I don't know what a transient is, but I know that we follow them. And there's kind of this feedback loop of information exchange, and there's directions, right? I think the things on the left are devices like LIGO and Virgo and these other detectors that are trying to generate information that then recruits people to do computations and thinking about these observations and maybe subsequent observations using different devices, and then we circulate back to try to refine that process. That's my understanding of it. What's key though from a computer science perspective is that the arrows that you see on this diagram, represent information flow, where information is being passed, data is being passed in various forms. Its provenance needs are different. Its access control needs are different every time it moves. The amount of time you have to store it is different every time it moves. There's a whole set of requirements associated with all of those arrows, and sort of the big vision for MMA is that all of those requirements, when the data moves between the entities in that previous diagram, use a single service. This is very much the cloud vision of things, that we can build services that are general purpose and scalable and secure and shared and cheap. And in this kind of futuristic world, these very sophisticated devices would use the same mechanisms that imaging telescopes would use to do follow-up, that the data brokers that are trying to make sense out of this maelstrom of data would use to communicate the sense they've made, that Toms would use to help with the recruiting of coordinated observation. Computer scientists would say there's no reason to have multiple systems for doing that. The concepts are the same, and we know how to build general purpose, cheap, reliable, secure systems at scale. Computer engineers are, more in touch with practice than theory often, and there's a healthy skepticism to be had, which we talk about, as to whether that actually is anything that could be accomplished. So it's, while if you're listening to the cloud hype, one ring to rule them all, but in point of fact, for this discipline, as near as I can tell, there's a couple of really important questions to ask. One, that single service really requires something called site reliability engineering, which, as near as I can tell, nobody in academia is prepared to do. It's very expensive. It's incredibly invasive. It doesn't fit with the academic mission, frankly, and it's incentivized, and it's difficult to incentivize academically. But this idea that you've got this magical service that you can call upon depends critically on this operational concept, and so until we can figure out how to do it, in an academic setting, it's not clear. It's not clear that we can pull this trick off. The other thing is that this Pubsub paradigm has a bunch of things built into it, which may or may not make it useful as a universal communication protocol, albeit one with very, very high level semantics in this case. And the biggest problem that I see at the moment is that the notion of topic is really attached to a notion of access control. When you subscribe to a topic, your access may be controlled to that topic, but most Pubsub systems that are topic-based do not have a way to further restrict access to information that is streaming and has been tagged by that topic. And it gets more complicated, obviously, if you're going to do some sort of join across topics. So it's not that it can't be done. And in fact, in our research group, we're working on this problem because it comes up in IoT a lot. And we think we have a solution, of course. But if you go and look at sort of the basic Pubsub things that are being used, and like Kafka and MQTT, those are two that come to mind. This is not easy to do if it's doable at all. And so it's not clear. It's not clear, in my view, whether we really want to try and build a single curated, consistent Pubsub infrastructure that this community could use. That would be wonderful if we could do it, because it would be much more long-lived, much more dependable. We could take a lot of the engineering out of the projects that and devote it to other more important concerns, for the project that we've seen. And this is hard, right? I mean, building one of these systems to be reliable is difficult because it's a full-on distributed system. But it's also, possible that you really need some of these things to be, more tailored to the task at hand. And then there's this question of Hopscotch, which in my view is really a future-proofing technology. Hopscotch is a really well thought out API at the moment that sits atop Kafka, but it insulates the users from what Kafka does specifically. Sometimes that insulation is thick, sometimes that insulation is thin, but the reason the insulation is there, they will tell you at the end of this talk, is because there are other ways to skin this cat, as we've been talking about. Kafka may or may not be the final solution that this community wants, or may not be the solution this community wants in different context, but having a single API, especially one that evolves as the community figures out what is utilitarian to do with a system like this, allows one to think about future-proofing what's going on. So I really view it as that as being the innovation and being an incredibly important thing to do, because these technologies are evolving pretty rapidly. That therefore brings us to the question of the Internet of Things. So here, if you haven't seen this yet, indulge me for a moment. This was the AI of about 2009. So when I started a cloud computing company about 2009, it was old hat. People were excited, the venture capitalists were excited, but what everybody wanted to look for next was this, not AI. It was not, the company was not called C3 AI, it was called C3 IoT, because this was going to be the next big thing. And there were people making predictions like 50 billion devices would be connected to the internet by 2019. That's 75 billion by 2025. This is a trillion. This is a trillion devices. If they're 1 watt each, just think about how much electricity that's going to cost. Trillion devices by 2025. The CEO of a major networking company actually made this statement. Our CEO started parroting it until I took him aside and said, "You're going to want to do the back of the envelope math here. This is not happening. Even if it does take off, there are some very serious technological impediments. But you can see that there was a great deal of excitement over this until there was a great deal of excitement over AI. Here's why, in my view. Internet search has been a revolutionizing technology. It's really changed society more than probably any other invention, maybe since the wheel or fire. And the reason is because it has changed human memory. It really has. People remember things differently post-Google than they did pre-Google. And it really is post-internet search rather than pre-internet search. And that has changed everything we do. That's changed the law. That has changed how we think about fairness. That's changed learning. That's changed, society. The Internet of Things is kind of internet search, but for human perception. It's really the ability to be able to extend what your senses gather. And there are people who are talking about more than your sense of sight, using digital technology. It's kind of the anti-matrix. It's not that everything's a simulation and you plug into it. It's that reality is instrumented and you're plugged into reality. And it's also immensely exciting to the e-commerce companies. The e-commerce companies are after what are called your preferences. Preferences are, in economic terms, some notion of what you will pay at any given moment for a good or a service. And knowing that and what good or service you wish to buy is the holy grail in e-commerce. And IoT ups the game for harvesting your preferences pretty amazingly. So today, if you think about the internet from an architectural perspective, it should look like this. It should look like a lot of centralized infrastructure. And that centralized infrastructure is pushing a great deal of data from the right side of the screen to the left side of the screen. Video, high resolution video, high resolution images, audio. There's content that's flowing from the cloud to your eyeballs. And every now and then, a very small amount of data comes back. But that small amount of data is incredibly valuable. And everything about it is incredibly valuable. Where it came from, when did it come, with what outgoing bits is it correlated? When does it happen again? These are the value is not scaled with the size of this data. It's a click. But when you click, the outgoing data is situated to be able to capture this. And you must capture it and you must not lose it. They're extremely rare. They're not very big, but in order to be able to figure out the value of these things, you really have to amalgamate lots and lots of them. And so big data and big stats, AI, is really about large, making large samples out of small samples. You want to do a categorization, and then you want the sample size in the category to be large enough so that you can make an inference. But the data that you're after, is really, really rare. And all of the cloud is architected to do this. So that's led to some things that I think are fairly entertaining. I don't think of this device as being a device that's in the top 100 devices I would want to automate first if I could automate things. It's not that complicated. I don't find it intimidating. I mean, I'm a little confused. What's the one on the top versus the one on the bottom? But after you rotate it a while, you sort of get the hang of this thing. That's $3.2 billion that Google paid to turn that thing into a robot, right? Nest took what seemed to be a perfectly reasonable technology, the thermostat, and added all sorts of surveillance technologies to it so that it can give you a great deal of, or it can give Google information about your preferences, along with other technologies like smart homes and these things that you speak with, so on and so forth. So so you can see that from an e-commerce perspective, there's a great deal of interest in this approach, but there's also scientific value, which is what we see now. IoT looks completely backwards from the way we've architected the cloud. There are going to be trillions of these devices. They're constantly saying something. So all the information flow is from the left side of the screen to the cloud. And every now and then, a very small amount of data goes back. And that data is important. If that data is turning something on or turning something off, it really needs to be delivered maybe just exactly once, if it's a safety thing. Also, the data sets are not huge here. These smart home applications where your refrigerator talks to your Nest thermostat to adjust its compressor usage based on the ambient temperature in your house, that's a perfectly reasonable IoT application. But the data that you're gathering for this activity is small. There's lots of these data sets, but what goes on in my refrigerator and in my living room is sort of meaningless in Boston or in Cornell, where Adam lives. The outside temperatures are different, and we don't, what Adam's personal habits are and mine, we hope, don't correlate. He being an erudite scientist and me being a computer scientist. So, this idea that it's big data in IoT is not right. It's lots of little data. There's a lot of it, but it's not that big. So, so IoT reverses the current cloud infrastructure. And this is sort of good news and bad news for MMA, I think. On the one hand, in our group, we talk about the SCiMMA project as the internet of really big things, right? These very, very large detectors are generating, that look like devices, and they're generating telemetry. It's important telemetry. You don't want to lose it. And then within some, temporal frame, we've got to respond to it, and we want to deliver the data, and we have to protect it. It has to be secure. There has to be provenance. There has to be access control. So, so it looks very IoT-ish to us, and as such, it may not fit the cloud as the sort of e-commerce formulation of it goes. But it's also different in that, from our perspective, there's a lot of producers and generally an equal number of consumers. In this MMA space, the producers are smaller and the consumers are larger. That's not, 100% true, but the number of devices that are generating these alerts that we want to do follow up on, for example, are not large by cloud numbers, and the payloads are big. These images, although Netflix and so on and so forth will deliver payloads, they will freely downsample them, and you kind of want the data intact, and that makes for larger payloads and harder QoS problems. So it's very, very interesting, and there's a lot of similarities to it, and I think the patterns match. But on the other hand, it's different enough to where I think efforts like SCiMMA are wholly warranted, and why I'm honored to be part of the project. Okay, this is my world. This is what I actually do for a living when I'm not on a SCiMMA meeting. We work with agriculture and ecology to try to build IoT systems in the wild. And this is a picture of a citrus orchard in Visalia, California. It's about 4 hours from Santa Barbara and about 1,200 miles from the nearest Amazon data center. And one of the applications we're working on is frost prevention. The little fan that you see there, that's actually about 1 kilometer away from where this image is taken. It's about 40 feet tall. It's driven by a large propane-fired engine. And when it freezes in this region, there's about a 6 or 7 degree Fahrenheit temperature differential from 35 or 40 feet down to the ground over here on the corner of this growing block. And so when that happens, you can prevent a hard freeze that will destroy these trees. By turning this fan on, it rotates around and it's pointed down slightly and circulating the warm air down to the corner of the block. Some key things to understand. One, there's no electricity, right? This is the nearest place where there's grid power. So if you're going to do anything around, analytics, when should you turn the fan on, for example, and when should you turn it back off, your sensing infrastructure is going to have to carry its own power as well as its own network. So this converged power and network infrastructure is a big computer science thing that we're working on right off the bat. There's some interesting challenges. But the other thing to understand is that this is done manually at night by people today. There is not an automated system for sensing this temperature gradient, turning the fan on, and ensuring that these trees don't freeze. The trees have about a 20-year life cycle, maybe even a little more than that, about 25. So they're a huge investment for farmers. When a farmer thinks it might freeze, what they do is they turn this fan on. It costs about $50,000 a night for the propane to do frost prevention here. And that's because they have to be incredibly conservative. And it's an industrial site. There's a crew out here. It's dark. This thing is a dangerous device. You don't want to be standing near it when it starts rotating. So there's safety concerns. I mean, it's very hard to do automation of this very simple problem in this space. And lastly, if you go and talk to the cloud people, and we did, I'll show you a slide in a moment, what they'll say is, yeah, you put a digital, a cellular modem here, and you put a cellular modem here, and you send the data for the temperature at 35 feet off to Northern California, 1,200 miles away. And then every now and then you send back a start message, and that start message starts the fan, and then you read the temperature here. And again, if one of those things gets lost and someone gets near this device and gets hurt, you have a problem. So you're not going to solve this problem by using a cloud and sending the data from the fan to the cloud to a thermometer here and back again. This is the simplest problem we could find for agriculturists. So it's a whole new world, and it really speaks to a whole new kind of computer science and computer engineering than people have thought about before. The other thing you have to do is a lot of engineering for failure, because things do not go well, shall we say, once you get out of the confines of the data center or the cubicle. The thing that's actually wrong here is not the fact that this looks like it's going to burn up. It's the fact that this is a carbon sequestration device. It's about a $300,000 flux tower, which was sited in a burn pit, a 100-year-old burn pit. You cannot measure the amount of carbon sequestration in the soil in a charcoal pit. How did that happen? IoT deployment is actually a programming activity, and the people who deployed this weren't part of the people who designed it. This happens all the time. So there are some real software engineering kinds of questions that need to be addressed, and they're very expensive when they fail. Although this one has a happy ending. They gave me that device. The first thing we did was reprogram it, and the second thing we did was run it out of power, because after we reprogrammed it, we started overrunning the batteries here. We're learning a great deal about how to do this. Now, the reason that we study this is because the technologists, the people at Amazon, for example, think this problem is solved, and no way is it solved. And here's how I will prove this to you. When we started doing this work, I said, okay, we're going to build our frost prevention control system out of Amazon to see how this is going to work. And one of my students is a brilliant embedded systems programmer, and he said, well, there are these great new microcontrollers. They've got onboard crypto, they've got built-in Wi-Fi, they've got a 500 nanowatt dormant sleep, which is really low. So you could put them to sleep and not use your battery. So you need very small solar for them. We should use these things. And I said, great, go make this thing, generate the string hello world, and have that string pop out in a MapReduce framework, Elastic MapReduce in Amazon. He said, okay. So first thing he had to do was port all of Amazon's IoT framework for microcontrollers to this new microcontroller, because they didn't have a port for this microcontroller. They do have some open source ones for common microcontrollers, but not for the ones we wanted to use, certainly not for the ones with the low power characteristics and the networking characteristics we want. So that took about 4 weeks. Then he had to become an expert in a networking protocol called MQTT. This person is an embedded systems programmer, not a networking expert. So he went off and learned MQTT and built an MQTT port to this. That was 2 weeks. In order to do that, he did that in order to interface this device to an SDK called AWS IoT Core. This is a bunch of Python code that's written so that any device that you wish to interface to AWS can interface to it. He's not a Python programmer, so he learned Python and then did that. In order to do that, he had to write an SSL module. And that SSL module implements Amazon's particular flavor of SSL, which is compliant, but not standard. And this was no end of fun, because until we figured out where that very, very fine distinction was, the Amazon people couldn't answer our questions about why we couldn't authenticate this device. That was a 12-week effort. Then he had to learn Amazon S3, which is the object storage system, because in order to use Lambda, AWS Lambda, the FAS thing that I mentioned, you need to use S3. And then from FAS, he could trigger computations of the Elastic MapReduce. Okay. If you are thinking of building many, many IoT applications, finding programmers who are facile, experts with this many technologies is not possible. This is not the answer. This is a placeholder. There is no way commercial software is going to work this way for IoT. What's going on here is that what you see in the middle here is the cloud. And the model that the cloud people have is that everything is a client of the cloud. In short, you make your IoT device a web browser. That's fun. It's a way to get something to work, but it means we need to do more research. So what are we going to do? We're going to build services. This is something that you're starting to see. Kubernetes is a microservice infrastructure for the cloud. What we want is a microservice infrastructure for everything. And that's because services are very efficient. They're reactive. They don't do something until you ask them to do something. They're incredibly reprogrammable. You don't have this sort of hardware built-in mentality that persists with IoT. Once you've built one of these IoT devices, you can't unbuild it or rebuild it easily, and that needs to change. And they're abstract. And we know a lot about how to manage distributed sets of services. So our thesis is that we really want to have an infrastructure that allows us to put services on devices. We built such a thing. It's called CSpot. CSpot stands for the Serverless Platforms of Things, and the first version of it itself was written in C, although you can program it in Python, Java, and these other high-level languages, but the infrastructure is in C, and that's because it will put a web service on a device that has 80 kilobytes of memory. 80 kilobytes. You can run a web server on something that runs on, a milliwatt of power, and be secure about connecting to it. It doesn't do much. There's not much that such a web server can do, but you can structure your codes using CSpot entirely as ensembles of services that are secure. It supports a functions as a service computational model. It has its own storage abstraction, which is portable and append only for robustness, and it's log-based, which means that when when your program is out there and there's millions of these events firing, you can actually figure out what the causal dependencies are, which is extremely important. But the way to think of it is, if serverless is microservices, is Docker and Kubernetes and these orchestrated, containers, these are nanoservices. These are that shrunk way, way down. It's open source, and we are thrilled when people wish to contribute, and we're building things out now. So we run this at UCSB. We run devices, and they run CSpot natively. We build small clusters, which we usually site in an outbuilding, and use either low power or long distance Wi-Fi, ubiquity Wi-Fi, to communicate. It will run these things will run CSpot. Then we run a fairly substantive cloud, the Aristotle cloud at UCSB, and it can run CSpot, and then we run in the public clouds. So you have this tiered architecture, and the whole goal is to move the data as little as possible, because as we mentioned, every time you move the data, there's a new set of provenance, a new set of access controls, a new set of QoS specifications, and your attack surface is bigger. So if you can compute out here on the edge, you should, for lots of good reasons, but you're very, very restricted in what you can do. So it's really capacity that drives how far up the hierarchy that you go. But the good news is that's a one-dimensional problem, and you can solve it pretty effectively. Interestingly, and I have seen this in the talks that I've attended as part of this auspicious group, the typical deployment here is really two deployments when you think of it from a Pubsub perspective. There's a data acquisition deployment, and we are just transitioning now, today, to where the CSpot stuff we do here has a Pubsub framework. Right now, it's messaging, which means every one of these devices has an address, and every server here that is acquiring data from it has an address, and we hard code the addresses. There's no notion of querying the system for where's the tractor, this kind of thing. But as I'll show in a moment, we're now building infrastructure for doing Pubsub in this environment. And typically what we do is we have one such robust collection, and then it communicates via a small amount of large throughput links to a data dissemination infrastructure. This is the thing that pushes the data to the users, and that has all the user scale, and often has metadata support. You don't want to spend a lot of time, querying metadata here if you can help it. You want to do your metadata kind of inference someplace else. So often this is kind of on site, and then this is either in on-campus cloud or in the public cloud. But the roles are really different. This is really about user scale, and this is really about data acquisition scale. And then you remediate them through some sort of Pubsub communication link. This is a picture of what we actually do, and the LCOGT people probably know this pretty well. We work at a place called the Cedric Reserve. This is an ecological preserve operated by UCSB. It's located in Santa Ynez, California, but it's in a pretty remote area. It's surrounded by agricultural land, but it's really an ecological preserve, and there's actually an LCOGT observatory there as well, because the night viewing is actually pretty good for the central coast of California. What's interesting is we have camera traps set up all over this place to look at wildlife and poachers and other visitors to the property as they walk by. And we can get to those camera traps using pretty high quality 100 megabit long distance Wi-Fi, but within a restricted area. To get data in and out of this site requires 3 microwave links. One that goes from the site up to a mountain that's located behind it, another that goes out to an island, Santa Rosa Island, and a third that comes into the UCSB campus. And it's ostensibly 100 megabits end to end, but I've never been able to get more than about 20 megabits from it, and it's lossy. So you have this interesting thing for our camera trap where we can do lots of processing out here. There's not much electricity, but there's some. But we have good quality networking within this remote region. We have bad networking that connects it back to very, very high quality computing resources. And we'd like to build a Pubsub infrastructure for that environment. The one we've done, which is the PhD thesis for a student who's about to get out, is a combination of a couple of different ideas from this space. One is a distributed hash table idea. There's a hash table technology called CORD. CORD is the idea that you can randomize an index essentially in a store and forward network using hash techniques. But you can prove log n search times in this circle by shortcutting the circle with a chord. using powers of 2 jumps. And this is really, really great work from the early 2000s. Proving that this is true is not easy, particularly in light of nodes coming and going and network partitions and so on and so forth. But it's an incredibly robust peer-to-peer lookup service. This was done back when Napster and these music sharing services were building these kind of ad hoc, very distributed, but very robust ways to find Britney Spears videos. And that wasn't an easy problem. So people were studying this formally. So what we've done is we've taken a cord network, but each node of the cord network is actually something called a raft cluster. Raft is a consensus protocol that will do strong consistency in the presence of lossy networks. It's got some latencies that are an issue when the networks are lossy, but if only one of the links is lossy, then the latencies are pretty low. So what we do in order to do Pubsub is we publish things to the ring. The ring randomizes where they're located, but we don't randomize where the replicas are for Raft. So we put one Raft node out at Sedgwick, one in my lab, and one in our cloud. And if you do that, this system is always up, even when we lose the microwave link, and the data is always available. If the data is being published from Sedgwick, we might wait until the Raft cluster heals. And there are protocols in there to do that, but we don't lose the data. Now, this Pubsub looks really different than Kafka. And it's all built from CSpot, so we can run it at any scale. But it's a really different way, motivated by completely different requirements, mostly around robustness and network partitioning, and the idea that there are regions of the network that are well connected, that are interconnected by poorly connected links. That Pubsub infrastructure looks different. And so what people ask us, what do we use Hopscotch for? What we use it for is to monitor that infrastructure. We actually use Hopscotch as part of a monitoring system that watches the CSpot components, because if you build your watching system out of the components that you're watching, you often get correlated failure. And this has proved to be true. Hopscotch has saved us a couple of times as we've been developing this system. But really, what we see it, again, as being useful for is future-proofing. We will put a Hopscotch interface on that Pubsub system so that we can then use it in conjunction with the wonderful Kafka packaging and deployment work that this project has done. If we want Kafka, today we just go and get Hopscotch because it deploys so beautifully and we understand the API. So we've seen a lot of benefit on the IoT side from the MMA investment in SCiMMA in ways that I had not predicted. And this is very organic. The way this came about was we needed an infrastructure to monitor our CSpot deployments. And we thought Kafka right off the bat, like everybody does. And then we started looking at how we future-proofed it and what we would do with respect to the deployment. And after about the 7th or 8th bullet point, I was looking at the last SCiMMA meeting notes, and I went, "This is just SCiMMA. This is just what we're doing. We're going to use it." So I find that to be very, very encouraging. I'll end by pointing out that our computer scientists, when they come to our lab, find that they're not working in a cubicle, and there's no free sushi. But there are lots of really tasty things they get to eat, like almonds. As you see in this picture. This is one of our deployments. This one has shut down. We were looking at differential irrigation. The question at hand was, does it make sense to water more or less on different sides of this tree at different times of the year, given the way that the sun moves in order to be able to save water? This is in Fresno. But what's important to note is that the infrastructure that we're using is in a pump house. This is an electric pump that services a reservoir next to this building, and it gets to be about 145 degrees Fahrenheit in this building in the summer. So we really have to build hardened systems to do this kind of research. But the thing that the students find strange is that they're spending a lot of time in the wild, working with these things, and not nearly as much time in front of their web browser in our lab, which is either good or bad depending on your perspective. This is our lab. I will stop there with a few minutes left to spare and take any questions that your patients might furnish. And thank you so very much for your attention.
Okay, and just before we take Jameson's question, Rich, thanks very much for that talk. I'll point out that Shireen there, one of your students, is in fact a former programmer for SCiMMA as well.
Yes, yeah, Shireen, yeah, and then she had the temerity to join our PhD program, which is great for me, for us, but not great for SCiMMA.
Okay, so Jameson, you have a question?
Is your question?
Yeah, so Jameson Rollins, you have a question for Rich? We can't hear you if you're talking. I think maybe Jameson is having audio questions. But perhaps if he tries to resolve that. I have one question, Rich. What are the sort of, you spoke a little bit about, things that may happen. If you were to pick like big things that might happen in the next 2 to 5 years in terms of technologies or new approaches, what do you think they would be?
For IoT or just in general, for the Pubsub stuff?
For the Pubsub stuff, or IoT, yeah.
I think this access control issue is a really thorny one. We see things like, I only want people to be able to see this data during the day. There's security reasons, there's industrial safety reasons. That's a hard access control IAM policy because it's temporally driven. IAM for AWS has lots of these rules that you can set up, but you can't easily set up a rule say that if this is the current conditions, these are the access controls I want. And for things like autonomous driving or the things that we work on, that comes up all the time. So I think that access control and provenance, which are closely related, are going to be things that the Pubsub community are really going to have to figure out.
Right,
and
yeah,
we're seeing it. Yep.
Yeah, I agree. We had the same conversation at SCiMMA, obviously, and we do have a, we do integrate with IAM, but that doesn't overcome the fact that topic-based authorization is not, you end up with many topics.
Yeah, no, and Andy is very clear, about this when he does his Tom stuff, where you've got these groups are willing to share this set of observations with those groups, but for this amount of time, that's real. That is an absolute real problem, and Pubsub is not architected as a set of abstractions to solve that problem yet. I think it will. I think we can solve it with that CSpot thing I showed you, and we do. So if we can solve it, others can.
Okay, interesting. Jameson thinks he has audio now.
Awesome.
Hey, can you hear me?
I can.
Great, thanks. Thanks for the talk, Rich. I'm trying to understand CSpot. I wonder if you could give just a brief description of it in the context of that the situation that you described about the microcontroller publishing to AWS. How does CSpot make that configuration better?
Yeah, CSpot just runs a web server, so you don't talk to AWS, you talk to CSpot. So you don't have to push it into Elastic MapReduce or into AWS Lambda and then serve it. You just serve it from the device.
But you're still. It's in the setup that you showed on the next slide. You still do have to build out more infrastructure between you and between the IoT device and AWS.
No, you would just fetch the data from the device into Elastic MapReduce in one step. Mm-hmm. Make a web request, a REST request to the device. Give me the data.
Right. So would you still call that a Pubsub then?
Well, right. So that example was not it was not a Pubsub example, nor was it a CSpot example. The Pubsub piece of it is so that we don't have to know the web address for the web service, right? So the way we solve that today, the way we solve your problem today, let's say we want to do a big computation in AWS over our devices. You have a client that runs in AWS that makes web requests to the devices. It populates whatever analysis technology it wants to use, and then runs the analysis in AWS. And those requests are REST requests. So it's just like talking to a web server in another cloud, for example, except it's on a microcontroller. Now, that has all sorts of, you have this URL, and you've got the parameters you have to pass. Pubsub abstracts those up to, I want everything associated with that device, and I want it every 10 minutes. And I'm going to do the authentication and the URL and so on and so forth once, and then the system remembers that and does the population for you. So Pubsub lifts the addressing, the discovery, these kinds of information management questions up a level. And so we built it on top of CSpot. But the key thing with CSpot is you're not doing 87 different technologies. It's just a web service.
Okay,
no one runs web services on their microcontroller. So running a web service in 80 kilobytes is tricky.
Okay, so thanks, Jameson says thanks in the chat there. Unfortunately, we are actually on the hour. So if anyone has any questions for Rich, they should post them on a $20 bill.
No. But by all means, email me. Absolutely. Thank you so very, very much. I really appreciate the opportunity to speak today, and I'm happy to engage. Post talk offline or next time we meet. Thanks again, everybody.